muted, just so that we don't interrupt our presenters. So please make sure that we are mindful of that as you come in. There'll be a little bit of time for questions if any after each presentation, so you can certainly feel free to unmute yourself and ask after that. Without any further ado, I'm going to go ahead and present our first group, which is coming up here. So if you guys can give them your full attention, that would be fabulous.
What's up? I'm Zane.
I'm Ria. I'm Gracie. Okay, so our presentation was about ocean acidification. So our experiment was based on goal number 14 of the UN sustainability problems, and it basically concerned conserving and preserving our ocean without doing any harm to the marine life. And the current issue that we've been facing for a while, since after the Industrial Revolution, is there is rising acidity of the ocean, and that's threatening the marine ecosystems. So if you can look at the diagram shown, it shows that carbon dioxide enters the water, it reacts with the water, and it forms carbonic acid. And then the carbonic acid reacts with carbonate ions, which is, it's basically stealing the carbonate ions from like clams and corals because their shells are formed out of calcium carbonate. So once they steal the carbonate ions, it forms into bicarbonic acid. And by stealing the carbonate ions from those creatures, it's threatening their lives, and they can't form their shells again once it's gone. So the entire cause of this rising acidity is connected to carbon dioxide emissions in our environment. And through our research, we learned that certain minerals can increase the pH of the ocean. For example, we figured out that olivine, which is a basic salt, and it's basically magnesium silicate, it can increase the pH of the ocean, as well as obviously if you add more calcium carbonate, since it's also basic, it would also increase the pH of the ocean. Now we're going to do a Kahoot. Okay, anyone on Zoom, you guys can join the Kahoot as well. Is there anybody left in class that needs to join? No? Okay. All the same people. Oh, there we go. Okay, so as you saw in the Kahoot, the carbonic acid dissociates into an H plus ion, and as we learned in class, as the concentration of H plus increases, the acidity will also increase, and that explains why the pH of the ocean has been decreasing. We have another question. So as you just saw, the projected pH for the year 2100 is 7.67, and the current pH of the ocean is 8.1, which may seem a little odd because we're talking about ocean acidification, but since the pH scale is logarithmic, there's supposed to be like a change of 0.01 over the years, and it seems small, but since it's logarithmic, it will end up becoming a very significant change in the year 2100. And on this graph, it goes up to the year 2010. And you can see that as the atmospheric CO2 increases, the level of CO2 present in the water also increases. And in accordance with that, the pH of the ocean decreases.
So the hypothesis for our experiment is that if the pH of the ocean water increases in the presence of a basic compound, then the use of minerals like olivine and tums will increase the pH of the ocean and combat ocean acidification. And then basically what we're doing here is we're just comparing tums and olivine, seeing which one decreases the acidification of the ocean more. And in addition to measuring the pH of both the solutions, we're also measuring the mass of the tums. And the reason we did this is because the tums is made out of calcium carbonate, and the shells of a lot of marine life is also made out of calcium carbonate. So it'll be directly like the marine life will directly it'll reflect this. And we did 2 rounds of testing. The first round of testing was just a general. It was very low pH, and it was just seeing whether tums or olivine did better in this. And the second round of testing, we measured the pH of the ocean currently, which is 8.1, and in 2100, which would actually be 7.67, not 7.1. And our procedure for this is that we started with 500 milliliters of water in a beaker, and we added 17.5 grams of salt to get a concentration of 35 grams per liter of salt, which is the same as the ocean. Then we added lime and Sprite as the acidity supplement. And as I said before, the first round was just a very high basic base test of high acidity, and the second round was with the current ocean pH and the projected ocean pH. And we used varying amounts of tums and olivine in these trials. The starting mass of the tums was 1.3 grams, and we measured that before and after 24 hours, as well as the pH, which we measured before and after 24 hours. And now we have is this right one?
So this is the results of our first trial we did. And this was the one where we had lime juice as our acidity factor. Sorry, I'm just trying to move this real quick. Okay. So as you can see with the first tum tablet and the second tum tablet, we did 1 and 2. And you can tell kind of, it's a little bit hard to see because of the color of the water. Since we added the tums, it did actually change the color of the water as well. So you can kind of see with the purple and the pink ones, which are the 2 tum solutions, that they did actually become more yellow, which was more basic compared to how it was originally orange, which indicates a lower pH using the pH strips that we had. And then on the right, you can also see that the olivine one did have a slight impact, but not as much as the other 2. This is kind of a chemical representation of what we ended up doing. So as Rhea stated when she was talking, increasing this concentration of H+ ions in solution actually will decrease the pH, making it more acidic. And also the calcium increases the basicity. So when we have that CaCO3 in the solution, it actually will make it more basic, which is what the Tums basically did. It's essentially calcium carbonate. So what we did was add that into solution, and it actually helped a lot. And I have a picture of a titration on here because it's kind of similar what we did. It's not a titration, don't get me wrong. But what we did is kind of similar in the way that we added something to solution to see how the pH would change over time as it became more basic. So this is a little bit more on why our data makes sense, and I'm going to talk a little bit more about the second round of testing we did as well. As you can see on the bottom, we actually tried to equalize the amounts of each thing that we used. So we tried to use about 0.5 ounces, which is about 1/20th of an ounce of everything in solution. And as you can see, the third picture is Tums. So that was very basic compared to everything else that we worked with. It was the only one that wasn't really at a neutral scale or more acidic. So the Tums definitely by far had a bigger impact than anything else we saw, especially with the olivine. So they both did increase the pH because of their basic properties, but because Tums are made of just calcium carbonate, it had way more of an impact. So this is a graph showing how our two test results paired up. It kind of shows how like olivine did have some sort of impact compared to like how much you added in, but not to the same amount that the Tums did. So basically there's just like the consistency between the two tests that we did. Both showed that olivine was not as strong as magnesium silicate would be. Oh, I'm sorry, that is olivine, as calcium carbonate would be. So the Tums did have this big impact because of the calcium carbonate that we had. And it shows here also that olivine did the same trend, but just at lower pHs. So there was an impact with both, it just wasn't to the same degree. And we also looked into the UN goal as a whole, not just what we could do to the ocean, but what we can do on land as well. A lot of land processes use CO2 emissions. And when it gets into the ocean, like Rhea described with her first slide, there's this reaction that produces calcium carbonate, and then it can ionize in the ocean, which is making it acidic, which is bad. So there's things we can do on land. However, it's a lot easier to tackle this from the ocean perspective and tackle things like that, because there's not much we can do that we're not already doing. It's very current right now. It's a very current issue to focus on CO2 emissions and greenhouse gases and try to fix that. So what we're doing does work, but there's also this obvious way that we can do calcium carbonate in the ocean. There's shells in the ocean that are made of calcium carbonate. There's a lot of ways that we can implement this. And I believe that that is it for us. Thank you. Questions?
Alrighty, we're going to switch over to our next presenters. And there they are. All right, you guys should be all set.
So this is the left side, which is still our left side. Okay, good.
The video is pointed to the center board.
We get into
Yes.
so you're standing. Yeah.
Okay. All right, so I'm Sadie. I'm Elena.
I'm Julian.
I'm Matt.
So our project is finding more sustainable alternatives to road salt. And the questions that we'll be addressing are what is an alternative to the common road salt that's more environmentally friendly? What's an alternative that is more sustainable and effective? And what's an alternative that is more environmentally friendly towards the vegetation?
Okay. So in the early month of February, Delaware County experienced heavy snowfall, which prompted the Villanova maintenance team to distribute large quantities of chloride-based salt solution on the highways, roads, and sidewalks surrounding our campus. While snow salt does enhance traction and prevent the formation of ice particles on wet surfaces, when the toxic salt solution splashes on nearby vegetation, it affects their roots,
affects their soil quality, and causes a major decline in their mineral nutrition. When plants are exposed to salt solutions for long periods of time, the salt accumulates within the soil, making the dirt so toxic that it can no longer sustain life for weeks to even months after exposure. Similarly, plants that come in contact with high concentrations of salt solutions are also more susceptible to biotic diseases and pests that make it nearly impossible for the vegetation to preserve its biological structures. The use of common Villanova road salt, which is a mixture of sodium chloride, NaCl, and agricultural-based corrosion inhibitors, contributes to the creation of biological dead zones that have a severely negative effect on ecological populations of plants and animals that surround our campus. Our group was interested in conducting an experiment based around snow salt and the negative effects that it has on vegetation in order to help us develop an improved salt solution that will not only melt ice on campus, but will also create a healthier system for stronger and healthier plants throughout the winter season. This experiment falls between the climate action and life on land UN Sustainable Development Goals and allowed our group to combat environmental damage by using key concepts that we learned in Chemistry 1156 this semester.
All right, so we initially believed that MgCl2 would be the best alternative, but after a bit of research, we found out that this was false. Our initial reasoning for this was because magnesium was found in chlorophyll, which helps plants with photosynthesis and helps them grow. But eventually that was proved false. So our hypothesis became that if we introduced MgCl2 into the soil, it would be more toxic than us introducing the road salt into the soil. And this would result in a slower germination period.
So for our variables and our constants, for the variables, we have our control group, which was just regular distilled water. And then the Villanova road salt, which we figured out was just a mix of chlorides and agricultural-based inhibitors and NaCl, so just salt, as well as magnesium chloride, and then the time of exposure to the solution. And then for constants, so everything that remained the same was just that we had to keep sure that the seedlings were exposed to the same external environment. So this meant finding a space where, temperature was the same as well as the same exposure to light. So we ended up using the greenhouse as somewhere where all of those constants would be stable. And then also it was just crucial that the concentration of the salts or the solution placed on the salts would remain constant each time we watered them. So we split our procedure into 3 parts to make it more organized. So for part 1, this was sort of just making organizing the cups based on letters and numbers, seeing which plants were going to go where. So A is just our solution for 8 weeks. B is the water for 4 weeks. And then all the cups labeled with a 1 are just pure water, so our constants. And then number 2s are 0.5 moles of the Villanova road salt. And then the 3s are the magnesium chloride solution. And then for the second part of our procedure was sort of just making the solutions themselves. So we just took 4 250 milliliter beakers and put 100 milliliters of water in each. We then calculated the amount of road salt which we would need, as well as the same of the magnesium chloride, and determined that we need 0.5 moles of each in their beakers of distilled water. And then each time we went to go water the plants, we would pour 16.5 milliliters of each solution into their designated solo cup. And we did this every week for 4 to 8 weeks, depending on the trial. And then for part procedure 3, it was sort of analyzing our data and coming up with those conclusions. So this was measuring the plant's height, which we did in inches, as well as the number of leaves. Pretty self-explanatory. We just used a ruler and measured from the bottom of the stem to the top, making sure we don't pull the roots out of the dirt because that would obviously damage the germination. And then we also made sure to average out the number of leaves on the plants because we didn't want to just make sure that the plants are growing based on height, but they're growing to their full capacity.
So here's our experimental data. So on the screen is a diagram of our plant orientation. If you look to the left, that blue section, the 4 cups, is just 8 weeks water. So we watered it with just pure water for 8 weeks. If you look to the lighter green pair, that's 4 weeks of water. And then there was another 4 weeks of the aqueous MgCl2 solution. The dark green is the 8 weeks of just the aqueous MgCl2 solution. Then the pair with the darker red is the 8 weeks of the Villanova road salt aqueous solution. And then the lighter red is the 4 weeks of water, and then the 4 weeks of the aqueous Villanova road salt solution. Okay, so we took pictures throughout our like per week to see like the growth of the plants. So from left to right, it's weeks 1 to 3. Week 1, the seeds were planted and watered, and as expected, nothing happened. Week 2, there was one seed that sprouted. If you look in the middle bottom right, it is the 4 weeks water and 4 weeks road salt solution. Then week 3, there were no sprouts, but the 4x4 road salt solution continued to grow more. Weeks 4 to 6, week 4, 2 of the 8 weeks water sprouted, and the 4x4 road salt kept on growing. And then week 5, there were no sprouts from the remaining seeds. The plants that already sprouted started growing a little more. And then finally, week 6, there was one new sprout in the 8 weeks H2O. And then the 4x4 MgCl2 and the week 8 aqueous road salt solution started showing some signs of discoloration. And then week 7 to 8, there were no new sprouts, but then the ones that were showing signs of discoloration showed even more signs of discoloration. And it turned out that only 5 out of the 12 pea plants that we actually planted actually sprouted. So this is a graph of our average growth of the pea plants. The growth is fairly linear as they sprouted and kind of goes with what we were thinking. So trial group number 5 led the height the whole time, which was actually the 4x4 of the road salt with the rest following. And then this is the average amount of leaves that were on the pea plant. So basically it's the same as the average growth, other than when trial group 1 shot up during week 4 and had more leaves in trial group 5, but other than that, it kind of averaged out to be more linear as time passed on.
Okay, so salt molecules are capable of absorbing moisture because salts are ionic compounds with strong intermolecular forces, and in this case, they were ion dipole forces. Thus, the ionic molecules attract highly polar compounds, which in this case is water, and they absorb the water molecules from the surrounding tissues of the plants. The salt within the soil that is absorbed by the seedlings dehydrates the sprouts' roots and shrivels their xylem and phloems. Xylems and phloems are the tubular tissues within the stems of the plant that are responsible for transporting sugar, water, and minerals and nutrients all throughout the system. Because these nutrient transport vessels are dehydrated, the diameter of the tube's opening of the xylems shrinks significantly, making it more difficult for the plant to get necessary minerals to undergo photosynthesis. Because of the decrease in the nutrient transportation within the stems due to the absorption of water, which is a reactant in the photosynthesis equation above, the plants were unable to yield an adequate amount of glucose and oxygen, which are products of photosynthesis, which were unable to develop more glycolysis, which is a process that's directly related to cellular respiration. Because there was a decrease in cellular respiration in the plants as well, the plants did not produce as much adenosine triphosphate or ATP chemical energy, which would then be used for other functions in the plant, which resulted in their death. The halt of photosynthesis and cellular respiration was directly correlated to the trial groups number 3 and 4, which were exposed to salt all throughout the 8 weeks of the experiment.
Okay, so we actually had to make sure that whatever we put on snow or ice actually had to melt. So we had to calculate the freezing point depression. So 0.51 degrees centigrade per mole is the cryoscopic constant for water. So we use that in our equation. To find the Van Hoff factor for Villanova road salt, we actually had to average what was the components within it because we didn't know the exact chemical makeup, like the whole composition and the percentages of what was in it. So we averaged it out to be 2.33. Doing the calculation for that, we found that the new freezing point for the Villanova road salt would be negative 0.69415 degrees centigrade. And then for the MgCl2, the Van Hoff factor would be 3 because it breaks into Mg2 plus and then two Cl minus ions. When calculating the freezing point depression for that, you get a new freezing point of negative 0.765 degrees Celsius. So that just proves that they would both melt the ice.
All right, so we concluded that our hypothesis was correct and that the NaCl2 would not be beneficial or more beneficial than the road salt. We said that the road salt was more environmentally friendly, although the discoloration was kind of iffy. And the negligible factors that we have to consider was giving too high of a concentration of NaCl2 or too little nitrates to counterbalance the Cl ions, and then not enough solution to the P's or an imperfect amount of like pea seeds to the plants.
So we actually have a pop quiz for candy. So get excited. So our first question, just raise your hand. If you're online too, feel free to like do the raising your hand feature. And we'll try to see you as best we can if you know the answers. So the first question is, what are xylums and phloems? Anybody? Ellie. Oh yeah, they are. There you go. Nice catch. All right, second one. This is going to be on the exam, people. Get excited. What is freezing point depression?
Chapter 12, I think.
Said a little bit.
Yeah.
We'll take it. We'll take it.
Yeah. All right, that's for you. Not bad. You guys want to take 3 and 4?
Yeah.
What is it? Sorry, Zoom is like in the way. There we go.
Okay, so what is one effect of salt exposure on the plants?
All right, they do. I'm not gonna throw it that far. Jordan's got it.
Oh, I saw that. I saw that. It's okay. All right, and then what makes NaCl2 a strong electrolyte? I mean,
Great question.
good question. Wonder who wrote that. No.
Dr. Guron, do you have this one? Okay.
There we go.
Yes.
Yes. Beautiful. All right, there it is. We'll give you candy too. Thank you. That's it.
Yeah. And then,
Exciting. Should we get all set up?
This is our last presentation, so just give us one moment to switch over. And here we are. Thank you, thank you. Loading, it's thinking about things. Come on, buddy. You can do this, I believe in you. I don't know why it says loading. Come on. It's just loading now. We're just loading. It was doing fine a second ago. There we go. Hooray.
All right, so our sustainability project was on cheap water filtration, and I'm Chris.
I'm Jack. I'm Colin.
I'm Connor.
All right, so our project basically focused on UN goal number 6, which was on the clean water crisis. And basically this is super important right now, especially in the pandemic, for people to have access to clean and accessible sources of water because of the current pandemic. There's an issue with sanitation and cleanliness for this COVID-19. And currently about 30% of the world population doesn't have access to clean water, which is a staggering number, especially in today's society. And this is mostly prevalent in third world and developing countries.
So a little more background. Seeing the crisis and knowing the lack of resources that's often presented in developing countries, we knew our filter had to be two things: it had to be cheap and effective. A low cost of production allows the filter to be easily made locally and also be made in large quantities. So we decided to turn to a familiar yet effective filter that's often used in schools by children, the classic water bottle filter. We also tried another alternative known as the tree branch filter.
All right, so for the water bottle filter, we kind of have on screen like basically what it looks like. So to construct it, you take like any plastic water bottle, you cut the bottom off of it, and you flip it upside down so it's capside down. And basically you just layer it with cotton on the bottom, then charcoal, then you have rocks and sand. And those are basically your four major filtration components. So basically how it works is we have the four components I just talked about. So the sand and the rocks don't chemically take anything out of solution, but they're used to physically filter out any like large molecules. And then the cotton's basically used to make sure that any of your filter components like the sand or the rocks or even the charcoal, if it breaks or chips into smaller pieces, doesn't get into your filtered water stream because that would contaminate your currently filtered water. And then kind of going into the chemical aspect of it. So charcoal is the only element in our filter that actually chemically takes anything out of it. So basically charcoal is negatively charged because it has this porous kind of texture to it. And we kind of have two examples of the kind of equations that would kind of go on within the reactions. So you have protons getting removed from solution, kind of seen with this equation up here. And basically that causes an increase in pH because you're taking H plus protons out of solution. And then we have an example with zinc, but this kind of equation can be used with a variety of different chemicals, and we kind of have listed down below the different chemicals that got removed with this exact same kind of equation. Just take out zinc and replace that with either, lead, iron, copper, and a variety of other minerals that we'll talk about later.
So our other filter was the tree branch filter. You can make this just by finding a branch from a tree, preferably a white pine, and removing the bark from it. You can remove the bark by either using a knife or any other tool you have. And then from there, you want to take the branch and insert it into a tube, and you want to fasten it with either a zip tie or any other thing you have lying around your house. And the idea here is that the branch's natural xylem, which is a porous tissue, will filter out the bacteria and any other contaminants. So how does this work? Well, first you want to use a white pine tree branch because white pine has a high concentration of sap compared to other trees. And the pores in sapwood, which contain the xylem tissue, evolved to transport sap up the length of the tree, which allows water to pass through while blocking out most types of bacteria. This process is osmosis because the pores in the sapwood are so small where the water molecules can fit through, but the atomic size of bacteria and other molecules are too big and get left behind. As you can see the picture up there, we have those green blobs of bacteria that get left behind in the branch as they pass through the branch filter. And also we cut the bark off the branch because the bark contains no sap, so there's no need for it to be in the filter. So how did tree branch or filter do in our experiment? Well, sadly, after 3 different trials, it did not work. In our first trial, we tried, we just went to a normal pine tree because we could not find any white pine trees on campus. And we used a dead stick. By this, we mean just found a branch of a pine tree on the ground and used this in our filtration experiment, but it did not work. So we tried using a live stick, which means we took a fresh branch from the tree and snapped it off and see if this would work, but it also did not work. So we tried using a different pine tree on campus, and it sadly did not work either. We believe you need to have exactly a white pine tree for the tree branch filter to work.
So before we can get started with our experiment, we had to determine 17 different criteria that we would be basing our water quality on. So you can see here in the picture, we use these test strips in the picture, and basically what we did is we would dip these in the water. You'll see a demonstration of this later on in the presentation. And from here, I'd measure 17 different qualities that we were looking for in the water. Now, a note to make about these qualities is that not all of them are bad. So you'll see as we go through some of them, like a higher concentration of something might be a good thing. A lot of these things are added purposely to water to make it safer to drink. So when I break these down, you'll see that not like just because we find a concentration of something does not mean that it's undrinkable. So you can see here, lead and copper are both natural elements, but they can oftentimes enter drinking water in older households or households where pipes are deteriorating through corrosion. And lower amounts are safe because they are natural minerals, but in higher amounts, they can lead to things like kidney and nervous system damage or nausea and vomiting in the case of copper. Continuing on, we have fluoride, iron, and mercury. These three things enter water naturally through water runoff. So these are a lot of things that we'll be looking at in like lower income countries who are poverty stricken and they might not have water sources like we do here, like drinking from tap water. These might enter water. If they're grabbing water from natural water sources like rivers or streams or things like that. So since they're natural, again, low amounts are completely all right, but in high amounts, they can lead to things like thyroid problems in the case of fluoride or kidney damage and mercury. Iron, again, is a natural mineral, so it can't pose too much of a threat in lower amounts to your health, but in high amounts, it can lead to household appliance harm. Continuing on, another big thing that we were looking at was total versus free chlorine. Now, free chlorine is sanitizing chlorine that is purposely added to a lot of drinking water and tap water that you'll see at water treatment plants. This will sanitize the water and make it safer to drink. However, on the other hand, total chlorine is the total amount of chlorine in the water. So sometimes more chlorine can be added than needed to sanitize. So that's where you get the total chlorine. So if the total chlorine, the amount of chlorine in there is more than enough to sanitize it, it can be damaging and it can lead to health risks. So that's a big thing to look out for. Hardness in water is the amount of calcium and magnesium in water. You can see the diagram there, the diagram of that. Soft water can lead to corrosion of your pipes, where hard water can lead to residue buildup. And then lastly, we have aluminum, sulfate, and zinc. Those are all naturally added to water. And then aluminum is actually added artificially sometimes to remove microorganisms, which we'll talk about later. So again, lower amounts are all right, but in high amounts, aluminum can lead to nervous system problems. Sulfate would be pipe damage and lead to a laxative effect. And lastly, zinc can lead to stomach cramps and nausea and vomiting. And these are our last step. So we have manganese that can enter water naturally, and in excess can lead to stained clothes and nervous system problems. Bacteria is a big thing that we're looking at. It can enter water through waste runoff. So if you have, like I said before, those like poverty-stricken nations where they're drinking from natural water sources, maybe if there's like a waste treatment plant somewhere nearby, or animal waste can lead to runoff entering the water, bringing this bacteria. So big things like that were E. coli, hepatitis A, and salmonella. And lastly, we have total alkalinity and pH that go hand in hand. We have the diagram there where most tap water is around a 7.0. It's a natural pH, but the lower you go is the more acidic water, and the higher you go is basic. Water can be found anywhere along that range, between like 5 and 9. You can see here some of the things, like I believe coffee is pretty low, down by 4. So anywhere in that range is drinkable. But for the purpose of this experiment, we're kind of measuring like most neutral water around 7. And then lastly, we have nitrates and nitrites. There are two different compounds that naturally enter water. An excess of nitrates can lead to what is known as blue baby disease, which is a lack of oxygen entering the brain. And then an excess of nitrites can stimulate growth of bacteria in water.
Now on to our results. I'd like to start by pointing out the light blue box labeled safe amounts. In order for a substance to be considered safe in water, it wants to be at or below that amount. If you don't see that blue box, it's because the safe amount is 0 or none at all. On this first slide, I'd like to point out one interesting one, which is mercury, which only the unfiltered water actually had any mercury, so our filter was taking the mercury out of the water. On the second one, the interesting one I'd like to point out is the hardness, where the filtered water was the only one that met our safety requirements, where our unfiltered water definitely did not, because see how high it is compared to our safe, but our filter was not safe either. This one, the interesting one, is all the way over on the right, the manganese, where only our bottle trial 1 had any manganese at all, but it still met the safety requirements. And on this last one, our pH all the way over on the right, all of those are within safe, but I also want to point out the lead, which only the unfiltered water sample, which you don't want to drink anyway, had any lead at all, so we were good. Now here's our interactive portion. We handed out your cups. If you have any water, you can pour it into that cup and then test it with a pH strip. We're going to also demonstrate that up here if you don't want to use your water.
I'm sure they can see you also.
Yes. Here, let me bring it up.
All right, so what you're gonna do once you have your water ready is you're gonna grab your test strip by the end with the like kind of excess paper, so you're not covering any of the squares with your fingers. And you're gonna dip it in your water for a few seconds, making sure all 17 of those squares are completely submerged. Hold it in for about 3 to 5 seconds, and when you're done, you're gonna lift it out. You're gonna shake off the excess water. You're gonna let it sit for about like maybe 30 seconds so the water can set, lay it flat so the water can be absorbed by all these squares. And then once you see a color change start to happen, you can start analyzing it on this graph here, I believe. So the way we have it is, you want to hold it with the excess paper end down and then hold it straight up like this. And then we're starting with lead going down. So this first square is lead, then we have fluoride, and then going down and then going down there. So for the people on Zoom, you can see this one here and kind of compare it to all the squares on the slide. As we're looking at it, does anyone see anything interesting about their water that they want to share? Any surprising findings? Ooh, lead in the water, that is not good. The school might need to invest in our water filters.
Lead in the water.
Lead in the water. So we're getting a pretty good finding of lead in the water. Whew. Right, so as you can see, there is like these contents in the water. So that's what we're hoping to address with these filters. We can go back to the.
It depends. You don't want too high amounts because then you can get stuff like kidney stones.
It should be like in the medium range.
Okay, for our conclusion, obviously we can't talk about the tree branch filter because of all of our experiments failed. But for the water bottle filter, we have plenty of data to go off of. It's shown to be not quite as effective as the filters in the US, minus like the water examples that you just said how you somehow have lead in it, because ours gets all the lead out. But it proves to at least be quite effective, which is one of our goals. And then it's also quite cheap based off of the materials we listed earlier. So it met both of the goals that we set when going into this experiment.
That's it for our presentation.
Any other questions?
So thank you to everybody who came out today. We really appreciate it. I have recordings of this available in case you need to take a look at it or want to take a look at it in a future time. And I hope everybody has a wonderful day. Thank you so much.